This is Spring Homework 01 Debrief for Math 3. Again, spring term. Today is actually June 28th, 2021, but I thought you students would like to at least see what this looks like. So there's a question on this first homework assignment. Again, this is Spring Homework 01 that poses this question: determine whether each function is an invertible function. In part A, they have L of x is equal to negative x. If you were to do a brief sketch of that, I hope you would recognize that that goes through, let me erase that and try it again, that this line has a value of x equals 0, y equals 0, x equals 1, y equals negative 1, and it is a diagonal line, slope of 45 degrees, slope of negative 1, that passes through the origin. That is this function. If it were invertible, then you would be reflecting it about the line y equals x, which I'm showing here as a dashed line. And if you were to hold a mirror up along this green dashed line and gaze into it, the reflection that you would see would be superimposed on the original line inside the mirror or behind the mirror. So in this situation, the inverse of this line will look the same. Now, formally, how do we assess whether or not it's invertible? We would reverse the values of x and y. So if L of x is y and negative x is the x side of this equation for the original, we replace x with y and we replace y with x. And then we ask ourselves, can we turn it around and make it into just one working functional equation? And so for that, I would divide both sides by negative 1. And that gives me y equals negative x. Now, this is the inverted original function. So it is invertible, yes, and its inverse looks identical to the original function, interestingly enough. All right, letter B. This one, if you do a brief sketch, is a coefficient of a that is less than 0. It's a negative coefficient. This part right there is what I'm looking at. And therefore, I classify this thing as a downward opening parabola. It goes through the origin at its vertex. To invert it, we would reflect it about the line y equals x. Again, that dashed green line. After you invert it, it will fail the vertical line test. Or if you like, before you invert it, it fails the horizontal line test, which signifies that no, it is not invertible. Formally, we would mathematically go y equals negative x squared as the original function, then replace y with x, replace x with y, and then rearrange this equation to solve for y. In this case, I would first divide both sides by negative 1. So I have y squared equals to negative x. And then I would take the square root of both sides, and I have y is equal to, my goodness, that would appear to be plus or minus the square root of negative x, which really does not work. Plus or minus the square root of negative x. The fact that it is both a positive and a negative root means it automatically fails the vertical line test. This function would only exist for values of x that are less than 0, since the square root of a negative number is imaginary for us. So if I could sketch the function, it would open to the left. And hopefully you can clearly see it would fail the vertical line test in this situation. So this thing is not invertible. Now, continuing on, if I really wanted to make this an invertible function, I could do that by restricting values of x to be only 0 and positive or only 0 and negative. It's my choice. If I restricted this to x being greater than or equal to 0 in the original function, then yes, this would be an invertible function. And as you might understand in a later homework assignment, the domain of the original function is from negative infinity to positive infinity before restricted. After it's restricted, the domain would become from 0 to positive infinity on the restricted original function. When you invert an invertible function, when you successfully invert a function, the domains and the ranges also exchange with each other. So in the invertible function, the domain of 0 to infinity on the original function becomes the range of 0 to positive infinity on the inverted function. And so, in other words, if I were to restrict the original function to be only positive values of x, then its inverted function would only be positive values of y. I'm attempting to, really, I am attempting to highlight that. So the purple for the original one and the green for the inverted function. But that's only after you restrict x to make it invertible. Since it was not restricted on this homework assignment, it is not invertible. Letter C. Well, this is a cubic function, and it's a flipped cubic function. So it comes down from positive infinity, goes through 0, and then goes off to negative infinity with an inflection point, as it's called, at the origin. So at x equals 0, y equals 0 is where it bends, bounces, and passes through the origin. Its domain is the set of all real numbers. The range is the set of all real numbers. Is it invertible? Well, it does pass the vertical line test. It also passes the horizontal line test in the original function. So that should be enough for you to declare that yes, it is an invertible function. Formally, if you take x and replace it with y, this would be x is equal to negative y cubed. I would divide both sides by negative 1. So negative x is equal to y cubed. I would then take the cube root of both sides. So the cube root of negative x is equal to y. Now this does exist. For example, the cube root of negative 27 is negative 3. The cube root of negative 8 is negative 2. So, I guess just enough experience will guide you on establishing that this is an invertible function. For all real values of x, there exist real values of y. So if I put in negative 1, the cube root of negative 1 is negative 1. If I put in, actually, it's negative of negative 1, I'm sorry. So if I put in x equals negative 1, then that becomes the cube root of positive 1, which is 1. If I put in x equals positive 1, then I'm evaluating the cube root of negative 1, the negative of positive 1, which is negative 1, which is another real number. So real numbers exist when you are taking the cube root of a negative number, and they exist for all real numbers. The sketch should also encourage you to believe that this thing is going to work. Again, using the green dashed line y equals x as the mirror about which this thing would be reflected. It passes through the origin. And what appears to be going up like that to the right would appear to be going up like that to the right. And in the mirror, when I look at the bottom part, it's going to look like it's going like that off and to the left. Let me think about that one a bit more. Yeah. Yep. Okay. Letter D. Is this an invertible function? Well, as a sketch, it's going to be, I'm sorry, I drew it upward. Oh, let's erase that before you see it. It has a negative coefficient, so it's going to be a downward opening product of a parabola times a parabola, which is just a tighter parabola. So if this were a normal parabola, then this would be x to the fourth power, for example, and then a minus sign in front of it. So if we get rid of this one, this is what we're dealing with. And is it invertible? Well, it fails the horizontal line test before you flip it, which means it will fail the vertical line test after you flip it. And if it were flipped, again, the origin is at the vertex of this thing. Then after being flipped, this thing would be opening to the left, and it would be pretty tight, and it fails the vertical line test. So, no, it's not invertible. Again, as before, if I were to choose to restrict the domain so that, for example, it begins at the vertex and goes up from there, then yes, this would be invertible, and its range and domain would swap endpoints. Letter E. Is this invertible? Yes. Why can I tell? Because every time it's an odd function, it's invertible. Letter F. Is that invertible? No. How can I tell? Because every time it's an even power, it's not invertible. Again, this is strictly for the power function. Yeah, well, okay, where I'm not worried about other terms, these are all monomial polynomials. So there's the short answer. If I were to do a sketch of letter E, then it would start at positive infinity for a negative value, come screaming down, bounce twice, and then go through zero, all at zero, and then go screaming down towards negative infinity as x becomes larger and larger and larger. Imagine that was the infinity symbol that I drew. Okay, so it's coming from positive infinity, and it's going to negative infinity as you go left to right. When you invert this, you might be able to just do it mentally in your head, reflect it around the line y equals x, and what do you see when you look in the mirror? So this thing is going to be coming up steeply, bouncing twice, and diving through zero, and then screaming up that way. Okay, so that's what the inverse looks like, and you can see after it's inverted, yes, it obeys the vertical line test. It passes the vertical line test. And finally, letter F, I've already established it and my reasoning. If you do a sketch of it, it is even tighter than x to the fourth power. It's opening downwards because of the minus sign. It fails the horizontal line test, and therefore it is not invertible. This concludes the debrief on, well, this was all spring homework 01.